when the kids
Welcome
I was about to tell you that's not professional.
to the 2015 Fall FE Review Session for surveying. See, Bryce could have got some humor. Okay, so we're doing surveying first. I'm going to record econ separately, so it'll be a separate file. So the portions of the reference handbook in version 9.3 that are relevant to surveying, you have the main surveying that's kind of embedded within the transportation section on pages 169 through 171. But then if you want the basic trig functions and the geometry functions for finding area and things like that, you got to go back to the math section, pages 22 to 26. So there's an estimated 4 to 6 questions, and these are the topic areas that are defined by the NCES related to the surveying topics. So we're going to talk about the majority of these. So angles, azimuths, and bearings are the main thing to understand here, how to take a line and find its azimuth or its bearing. So azimuths are generally in a clockwise direction, so starting with north as 0 and going around clockwise up to 360. 360 and 0 are the same thing, so technically it goes up to 359.9999. Bearings, so you always have a start with the north and the south designation, and then the angle is going to be referenced from north and south, and then you're designating if it's in the east direction or the west direction from north and south. So let's find the azimuth and bearing for each of the following. So for A, what's the azimuth going to be equal to?
70.
So it's going to be directly equal to 70 degrees. What about its bearing?
North 70 east.
So this one's measured from north. You have 70 degrees east. What about B? Azimuth.
145.
So you got that by?
90 plus 55.
So 90 plus 55. Bearing?
South 35 east.
So looking for this angle here, so 180 minus 145 gives you 35, and it's measured to the east. C, azimuth?
350.
Sounds right. So 270 degrees plus 45 gives us all the way around 315 degrees. Bearing?
North 45 west.
So north 45 degrees west gives us that angle is 45. Azimuth for D.
260.
So with this whole angle, so 180 plus 80 is 260 degrees. And the bearing?
South 80 west. What is the likelihood of just getting a question? When they straight up just ask for the bearing and or azimuth?
I mean, it seems pretty reasonable.
It's quick.
Yep. And hopefully everybody remembers how to do the degrees, minutes, seconds conversion on your Casio. You've got the button that's degrees, minutes, seconds. So you push the degrees value, hit that button, enter in the minutes value, push that button again, then enter in the seconds and push it again. And then hit enter, and it will automatically interpret it as degrees, minutes, seconds. And then if you push the button again, it'll toggle back and forth between degrees, minutes, seconds, and decimal degrees. So any questions on azimuths and bearings? Area computations. So in most of you had me for geomatics lecture, didn't you? Anybody have it last semester? You got it last semester. Went over the same content. So we really only talk about area calculations when we get to the end of the semester when we're talking about volumes. And so we were typically looking at some sort of cross-sectional view of a roadway, and trying to determine the area of that cross section, and then knowing two cross sections that allowed us to calculate the volume in between. So these are the formulas that the FE review manual give you for calculating areas, and this is in the surveying section. Obviously, you get the other basic area calculations in the geometry section. But the first one, the area by coordinates, assuming they gave you something about the coordinate system, and so you had x, y corresponding to these 4 points here. You could use this equation that's shown here to solve for the area. The trapezoidal rule, so if you have a shape that is a trapezoid, let's see, you have your heights. Just should remember this, and at least should have looked it up. You have your heights of your trapezoid, and then the W, the width. I can't remember if it's that one or that one. They don't give you a picture that goes along with this. Let's go off the reservation. The value of carrying your life around on a USB drive. And this is a different trapezoid calculation, isn't it? H times B1 plus B2. The coordinates. Yeah, I think it is the bottom of that shape.
I would think so, because it said in the beside that in the slides that you're on, that W is the common interval, and if it's an irregular shape, then in the FE slides.
Oh.
Maybe.
Yeah, so so I guess you have your two heights. So it is, this part of it is consistent with that one slide that we were looking at. So if you have two different heights, and then you have the width here, still doesn't quite make sense. Anyway, we'll carry on in the interest of time. So Simpson's 1/3 rule, and I'll get back to you on that if I don't figure it out when we're going through the sample problem. Simpson's 1/3 rule. Yeah, we don't use that in geomatics, and I'm not in my example problem doesn't address Simpson's 1/3 rule either. But kind of when you use each one, so if they give you the coordinates, obviously the area by coordinates is the best route to go. Yeah, so the trapezoid rule, if one side of the area has an irregular shape and can be divided into a series of cells of equal width and irregular side that is fairly straight. So on a roadway cross section, that's typically going to be the existing ground or the upper elevation or the upper line. And then, if you have parabolic sides, then using Simpson's 1/3 rule. Might be one. If they tell you to use Simpson's 1/3 rule, you can figure it out on the exam. All right, so boundary and traverse lines bounding an irregular area are shown below. Estimate the total area. So we are going to try to stumble through. This can be painful. So using the coordinates method, and I apologize that I do not have the solutions to this. But if we assume in terms of coordinates, we've got 0, 0 here, then this is going to be 0, 34. This would be 30, 0, 60, 0, 90, 0, 120, 0, and 150, 0. So then we're going to have 30, 21, 60, 23, 90, 29, 120, 31, and 150, 23. So using the area by coordinates. Let me see if I can remember how to do this. So if you set up a table of your X's and your Y's, so you're going to have, let's do A, and you want to do it in a clockwise manner. So we got A, B, C, D, E, F, G, H, I, J, K, and L. So listing those in order, so we have 0, 0, 0, 34, So our N in this case is going to go all the way up to L. I know there's a, let me switch back over. Yeah, see, the area calculation by coordinates that we go over in geomatics is a different. We don't use that equation. We use the this method where after you have it laid out, so you're going to take the products, so multiplying. Here it is. So this first calculation would be 15 times 858.9 would give you that. Then 858.9 times negative 33.8 would give you that. So you multiply these all the way down through and sum each side. So in our example, then after you sum those, you're going to take the sum of the minuses minus the sum of the pluses divided by 2. Yes, you end up doing the difference between those two. So over here, if we do our, what was it, minus and then plus. So the first one, we're going to have 0 times 0. That's just going to be a 0. Fast. And it looks like the very last one is repeated at the bottom. So we're going to have another A down here. All right, so we've got 0 here, 34 times 30, 9. So then 21 times 60, so we're just going this direction.
1260,
23 times 90,
2070,
29 times 120,
3840, 4650, 3450,
so then we've got zeros the rest of the way down. Sum of that row.
$16,290,
16,290. So now we go through the other direction. So this one's going to be 0, 0. Then our first value is going to be 30 times 23.
690, 1740, 2790, 2760, zeros.
So then summing that one,
$79.80,
so taking the difference between those two, so 16,290
$83.10,
divided by 7,980 divided by 2,
$41.55,
what's 150 times 30? 4,500?
40, yeah.
Okay, so that at least is in a ballpark that seems like it would make sense. So obviously on the exam, they're not going to give you a shape anywhere near this complex if they want you to do the coordinate method. And I'm sure they would give you an option as to which method you want to do. And since you should be able to reasonably approximate just looking at the shape. Therefore, I would say that all the answers they give you are at least going to be in the same ballpark. But going through and doing this coordinate method should give you a much more precise answer. And it's not that difficult once you remember how to do it, which I clearly didn't until I looked back at the slides.
So is it going to matter what you call positive and what you call negative?
No, I don't think so.
Not going to take the absolute value.
The only reason it gets tricky, or it got tricky in the example for geomatics, was that the way we set up the coordinate system in this example, the center line was at 0, so you had negative coordinates, and that's where you do have to keep track of your signs going down through, because then you're going to end up with values canceling out. And so it does, if you do have negatives in your coordinate system, then you do need to keep the signs, and you still end up adding everything together. You definitely need the signs, because a negative 30 times a 30, yeah, you want to maintain the signs going through. Okay. And so then these both end up being negative, and that's why, but when you subtract them, you'll end up getting the difference between them. Okay, let's see if we can figure out the trapezoid. So we got the trapezoid equation. Let's see if we can figure out how to apply it here. So in this case, my writing utensil. So for the trapezoid rule, we're going to calculate the area of each one of the trapezoids. So we're going to have our base, which in this case is 30, so that is consistent for each one. So this first, so we'll number them through 5. So we'll have 5 calculations. So we have 30, and then we have height 1, which would be 34 plus 21 divided by 2. And we're going to, and since we do have that uniform width of 30, we can just add these together. So then the next one would be 21. Is that right?
Is that gonna come up with the exact same answer? I would assume not. Which one did we choose?
Actually, so this is showing that H1,
If you do it like that, the H1 and HN, and just not dividing the other ones, you get 39.75.
yeah, the trapezoid rule could be more of an approximation. Let's go through and calculate each one of them. So this would be 21 plus 23 divided by 2 plus 23 I'm going to erase this.
That gives you 39.75 as well.
So then it's not an approximation.
So you could just do the first one minus the last one, and then not divide any other ones out.
I guess somehow that math works out. I'm not.
Well, because you're adding 21. Oh, I don't know.
It's too late to try to derive it's definitely beyond my mental capacity to try to derive equations right now. All right, so Simpson's rule. So we have H1, HK. So somehow that's, if you have an odd number of trapezoids or an odd number of measurements. So in this case, we have 1, 2, 3, 4, 5, 6. Assuming those verticals are the height measurements, we would need to have an odd number of measurements. So we wouldn't actually be able to use Simpson's rule in this case unless we disregarded this last section so that we had an odd number of measurements. So maybe we had a slight miscalculation somewhere over here in the coordinate method because they should both give you the same answer. But at least you get the idea. Did you discover the mistake? Did you have an aha moment about something different?
Well,
Okay. I have those all the time. I shouldn't be the one that's having it right now, though, since I'm the one running the review session. But yeah, so the Simpson's rule, if you were to use it, then so you're taking H1, which in this case would be 34, and then you're taking 2 times H, the sum of 8 of the odd. You would have W is 30 times 34 plus 2 times the sum of H3 and 5, so that'd be 23 plus 31, and then plus 4 times the even ones, which is 21 plus 29. And then that whole thing divided by 3. So that's the 1/3 rule, but again, we'd have to basically ignore this last section and calculate it separately. So that would be more applicable if you had a whole bunch of values to use, or a whole bunch of segments that you're trying to calculate.
you could just add the last one in at the end. It says plus HN.
Well, but it's still, actually, no, I missed that. So in this case, it would be 31. That's what HN is.
Oh.
So because it says there that N must be odd. And even on my explanation, it says there has to be an odd number of measurements or an even number of intervals. So we have an odd number of intervals in this situation. All right, now that we butchered that problem, let's move on to earthwork and volume calculations. So again, the area calculation is typically if you're trying to calculate the area of each of the cross sections, and then you use the earthwork formulas to figure out what's the volume of the area in between. And so the area calculation should be precise as long as it's a normal shape, or sorry, as long as you don't have any parabolic or curved edges. Because if they're all connected by straight lines, then the coordinate method is definitely going to give you the exact answer. The volumes, on the other hand, are approximations when it comes to earthwork because it's never a solid straight line in between. It's always something curved, and it's not necessarily going to be a uniform segment. So the methods that they give you the equations for are the average end area method. So if you have A1, if you know what the cross-section area is for those two, you're just multiplying times the length between the two sections and dividing by 2. The prismoidal formula is if you have some reason to believe that there's a significant change at the midpoint between the section that you're interested in, say it's widening out or narrowing in, and you can approximate the area. So A sub m is the area of some midpoint in there, and it should be roughly halfway in between A1 and A2. You can plug that in, and the prismoidal formula is supposed to give you a slightly more accurate formula because it's accounting for that midpoint section to be different. Then the pyramid or cone calculation comes in. Say this, my drawing skills are horrible, but say this last segment tapers down to nothing. And so you would have a section here, looks like a fill section, so assuming the road's being filled in, but then at some point that's going to taper off to nothing. So this section ends up being a pyramid or a cone. And so the volume is going to be the area of the base, which if we had an A3 here, we would have A3 here, and then what is the height? No, the height would be this distance. That would basically be the L up here. The L for this calculation, it's the same. The distance along the roadway basically would be the height. So that's easy to get confused whenever you're trying to use that calculation because it's not a vertical height. It's actually the length along the road. So if we have earthwork quantities for a section of road that are shown here, the transition section, so a transition is where it's going from no fill to having some fill, or no cut to having some cut, or vice versa. We can assume that those are triangular in shape. We want to calculate the total volume of cut and fill. So let's start off at station 20 plus 0, 0. So we have no cut here, so we're not going to be calculating any volume of cut. And actually, so our areas correspond to the station, but the volumes we should be putting on the rows in between, since they're happening in between the cross-sectional areas. So we're not going to have any cut volume here. Our total fill volume, we can use the average end area, A1 plus A2 divided by 2 times L. So what's that going to give you for the first one? So we would have the length between those two is what?
10.5.
So 10.5, and then 173.21 plus 43.56 divided by 2. let's fill out the fill volume all the way down before we deal with the cut. So then between the next two, we've got, let me write the calculation here. So our distance is going to be 11 feet. And then we have 43.56 plus 9.63 divided by 2.
293.
So what about the next section? Is there fill between 2150 and 2845?
Okay.
So do we have anything here?
Is the pyramid?
Yeah, so this is what's called a transition section. So something has to happen. They're not just going to cut off the fill and have a wall there holding it. It's going to taper out to nothing. So this is where we're going to use the base equation, height times area base divided by 3. So in this case, the height is going to be what? 6.95.
Area.
6.95 times the area of the base, which in this case is 9.63, and then divided by 3 for the area of the pyramid.
22.
So then we don't have any, so there is no fill volume here. So what's that give us for the sum of fill?
$14.53.
So then the cut works in the opposite direction. So we have the transition, so nothing between 20 and 20 plus 1050. Then here we're going to have one of those transition sections. So we have 11 times 14.32 divided by 3. So then we go back to the average end method. So our distance 6.95.
$2.75.
And then another average end, so that's going to be, what, 11.55? No.
Yeah. $14.56.
So the sum of the cut's going to be 1784. So then if they ask what is the difference, like is this job going to have more cut or more fill, you can just take the difference of those and figure out which is going to have a higher amount, whether you're going to have to bring material onto the site or take some extra material off the site. Any questions on that one? Audience at home? All right, so the next topic is leveling, and the type of leveling we did in geomatics, and the most common type is differential leveling. So this is determining the differential elevation between 2 points by taking backsite and foresight readings on a level rod. So there are no equations in the FE reference manual for this, so I guess you just have to remember these. But the typical problem, you have an instrument set up somewhere, you have some sort of benchmark that you're using as your reference elevation. In this case, it's BM rock that has an elevation of 820, and you're trying to find the elevation of point X. So HI in this case corresponds to the height of the instrument. So HI is the height of the instrument. So we're going to start with the elevation of 820. You're going to place the level rod there and take a reading on the level rod, which would be this 8.42 feet. So to get the height of the instrument, you're going to take the benchmark, which in this case is an elevation. So you're going to take the benchmark elevation of 820 and add that backsite reading to get up to the height of your instrument. So backsites are always added. So backsites are also called plus sites. So this will give you an instrument height of 828.42. That's really an arbitrary distance. Then you're going to move the level rod over to the next point, rotate your instrument, rotate your auto level around, and then you're going to take the instrument height and subtract out the rod reading so that you get back down to the point on the ground. So the elevation of that point is going to be equal to your height of your instrument of 828.42 minus that foresight reading, which in this case was 1.20, and that gives you an elevation on the ground of 827.22. Closure is the amount of error that you have in your survey. And so this would be this type of data collection shown here. This is just one measurement. If you had another point up here that was the ultimate place you're trying to find an elevation to, you would then have another instrument set up. You would take another backsite reading. You would set the level rod up here and then take another foresight reading. And so you would just keep repeating these HI and elevation calculations until you find the elevation of the final point you're interested in. Then what do you do? Or what did we do in geomatics? So the fountain was usually the point we were interested in, but did we stop when we got to the fountain?
No.
You came back. So we would run what was called a loop. So you go out and you come back, because if you then survey your way back, you're going to be able to calculate the elevation of your original benchmark again based on all your backsites and foresights. And so if after you go through all these calculations, if your final elevation, if in this case it didn't equal 820.00, what's that mean?
It wasn't being John.
Nice. See, Bryce is missing out on all kinds of comments.
You had error.
That means you have some error. So the ways that you can calculate the error is, I show benchmark calculated minus benchmark known. It's also benchmark final, the final observation versus or minus your initial one. Also, if you have a set of data corresponding to this, you have your backsite column, you have your foresight column, those values. You sum the backsite column, you sum the foresight column, take the backsites minus the foresights. This will also give you your closure. So you can calculate it both ways, and you should get the same answer both ways. The last part is then taking that error, that closure error, and distributing that error to all of the elevation calculations. So again, I don't know how detailed the a problem you might get on this on the FE, but this example will kind of go through each of the steps. So calculating the HI. So here, again, HI is equal to the elevation. If we have a starting point of 100, so this is our initial BM1, we're going to add the backsite. So we would have 100, and right there. Let me write the calculation over here. So 100 plus 5.510 equals 105.510. So then the elevation that we're calculating, so the HI, and you can kind of imagine these are instrument setups. So in between BM1 and TP1, TP stands for turning point. Nice. So in between benchmark 1 and turning point 1, that's where you had your first instrument setup. Then you have your second, third, and fourth instrument setup. So when we calculate an elevation, we're interested in the elevation of our actual points on the ground, which would be the TP1, BM2, in this case, TP2 and BM1. So elevation is going to be equal to our HI, 105.51, minus the foresight of 3.25. That's going to give you
102.6.
102.26.
26, yeah.
102.26. So then our next HI is going to be 102.26. So the previous point on the ground, the elevation, plus 6.530.
108.79.
You already got all these calculated.
98.29. 102.61. 95.94. 99.21. 91.32.
So we'll check Jacob's math. So we can now sum the back sights.
$19.63.
And the foresights.
$28.31.
Is this a survey you guys did?
Probably.
So our closure error would be 19.63 minus 28.31.
That was probably our second competition. Negative 8.68.
So negative 8.68. Whoa, screen's a little shaky at the top.
You don't have the label above elevation, but that's in many inches.
Yeah.
So that's really good, actually.
So we can also calculate closure by taking the final, which is 91.32, minus our initial, which is 100. And it looks like that gives you negative 8.68. So that means the HI and the elevation calculations are correct. So now we have to calculate the adjusted elevations. Anybody remember how to do that?
Take that, divide by the
Divide by disclosure or disclosure somewhere.
Adjustment equals
total amount of
closure error divided by what?
I thought it was horizontal.
Well, so if you have, there's two ways.
Turning points,
Yeah, so no, close.
number of stations.
Number of station setups. So if you have, there's two ways. There is the uniform or the equal, where you just divide it equally depending on the number of instrument setups. If you have horizontal distance information for the back sights and the foresights, that's when you can use the weighted distribution. That's when you divide by the total horizontal distance surveyed, and then you apply the adjustment depending on taking that adjustment times the horizontal distance for the back sight and the foresight. Here I'm just looking for the number of instrument setups. So we would have, so our adjustment needs to be positive. So if we have negative error, we need to add those adjustments. So it would be plus 8.68 divided by 4, which would be 2 point something.
17.
So then our adjusted elevation here is going to be equal to what? So for this one, we can take 102.26 plus 2.17.
104.43. 100.46.
So how do we get the next one? Because this is always the common mistake that's made.
You have to subtract it. Add double that. Maybe, I don't remember.
So the best way to remember, because this applies to both the equal distribution and the weighted distribution, is to just re-add the backside, subtract the foresight. Start with this, so it would be the one we just calculated, 104.43. The common mistake is to use the original one. But if we take the one we just adjusted, 104.43, plus the backside again, 6.53, minus the foresight, 10.5, and then adding our adjustment of 2.17.
2.63. Is that not also the same as adding the adjustment twice and 3
Yep.
times?
But I stopped teaching it that way because students couldn't remember how you do the weighted distribution calculation, because it doesn't work that way for the weighted distribution. What's that one give you?
102.45.
So if we did it right, it should equal the initial. So we should be able to get rid of the error. So in this case, it did. Questions on that? So obviously they're not going to have you go through this many calculations, but they could give you part of the table similar to what I did on the exam. I'd give you parts of this. I'd give you this table, but there'd be blanks in there that you would have to figure out how to calculate what was missing. Everybody got that? John, you got it?
Yeah.
So closure also applies to traversing. So traversing is where you have a boundary that you're interested in, and you would set your instrument up on each of these vertices, directly measure these interior angles as well as the horizontal distance corresponding to them. Then the only thing that the FE book does give you is it reminds you that latitudes are the north-south and the departures are the east-west. But the latitudes and departures, whatever you pick as your first point, so if this is your first point, the departure is going to be the delta x so positive and negative. So if you sum all of your departures for a full traverse, they should equal 0, because you should be going the same distance in the x and coming back if you don't have any error. And then the latitudes are just going to be the delta y, which again for a closed traverse should, if you sum that column in your data, should equal 0. And then in class, we would then take that information and calculate the coordinates, assuming some initial coordinates of your first setup. So they don't give you the equations for the latitudes and departures, but if you have a point and a distance L, so this would be your delta X, this would be your delta Y. So our trying to think of the so certainly delta Y is going to be equal to L times the sine is opposite, so it'd be sine of alpha, assuming this is alpha, and then delta X is going to be L cosine of alpha. But I'm trying to remember, it seems like if you already know what the azimuth of this line is, that you can directly use the azimuth in this equation, and it figures out the sine and cosine will automatically assign the correct positive and minus. So if it's a positive, if you're moving to the right, that'd be a positive X, and if you're moving to the left, so if the angle is, if the azimuth is greater than 180, it will automatically give you the negative sign in the calculation. But we will try these as our delta X and delta Y calculations. And of course, we have a bearing and not an azimuth. So assuming we have this polygon closed traverse from point B to point K, and we have the known coordinates of, actually this says point K. Oh,
Different.
okay. Okay. Yeah, so we're going to go through and calculate the coordinates of point K. This is a screwy problem. Who came up with this one? How would it be a closed traverse if it doesn't, if the first and last point aren't the same point? What's that?
Now you know how we feel.
Let's just add another row.
Yeah, so but theoretically it's not a closed traverse if it doesn't close around on itself. So we'll scratch that out. So a traverse is run from point B to point K, and we have some known coordinates at the end for comparison purposes. Actually, I do have the equations on here, but so the departure, let's try to draw this. So this is north and to the east. So if we've got point B here, point C is going to be somewhere up here. So what does L sine of, well, so this angle, so departure is delta X. So in this case, sine would give us the right thing, because that's going to give us our distance here. So what's 487.52 times the sine of that angle give you?
53.62.
And then cosine?
462.69.
So it makes sense that at that angle that our delta Y is going to be much larger than our delta X. What's that? That's supposed to be an arrow showing the angle. So then point D, we're now going south and to the east. So that's going to be heading off in probably not quite that steep of an angle. So point D is over here. So go ahead and plug, use the same, so 87.
788.2. 0. Negative 39.01. 809.72.
Here, hold on. Let me think about this one. So our latitude is our delta Y. So we got delta X, delta Y. So X is definitely still going in the positive direction. Y, we're definitely going down.
Yeah. It's only 92 degrees.
Okay.
Barely go down.
And so did you plug 8710 in?
Yeah.
Okay. So then the next one's,
Well, I plugged 9250. Because that's southeast, not northeast. So you gotta add 90 to that.
let's see, now, so that angle is this angle, right? So the sine of that angle directly would give you
Actually,
this delta x.
yeah.
So plug the 87, we still want to plug the 8710 in. Hopefully you're writing in pencil.
I'm not. No, that's all right. Sorry, bro.
What?
Never write in pen. I burn erasers up for a living.
Carcinogen.
88.20. So the same thing.
And what? That was the same?
Yeah, that one's the same. And 39.01, so that's the same as well.
Negative.
It just didn't give me the negative this time.
This time. Okay. So the value, the 92, would be the actual
Yeah, it gives me
azimuth.
the negative.
Okay. So if you use the azimuth, it will give you the negative, but if you use the actual value, you have to, what was it, negative?
Negative 39.01.
So hopefully if you're using pen, you didn't scratch it out before you found out what the answer is.
I did.
So if you use the azimuth, it will give you the right sign. If you don't use, if you use the bearing instead, you're going to have to draw it out and figure out what the sign is. So then the next one is going to be further in the same direction at a little steeper slope to get to K.
809.72 and negative 163.02.
All right, so now we can sum these. No, actually, can we do that? Yeah, we could sum them, but it's not going to tell us anything because this isn't a closed traverse. If this was a closed traverse, we'd be able to calculate our error at this point. Since we don't have that, we're now going to have to calculate our error based on our final K value. So if we want to know the easting of point C, how would we find that?
You just add your departure to your space.
Yep, so now if we add plus 153.62,
8908.94.
and plus 788,
96.97.14.
96, 97.14.
11316.58.
So we can see that there's some error there because it should now match up with this 1151.15. Let's go ahead and do the northings.
$11,713.3.
And the next one's going to get subtracted. It's a negative.
11,674.29. $11,511.27.
Oh, so actually that's the one that gets compared. How's this so far off? Check that last calculation. So that should only be 10,000 something.
$10,506.86. I don't know how I got that.
All right, so now the linear misclosure. So we have the K that was surveyed that has these coordinates. So K is surveyed 10,000, 506.86, comma, 11,511.27. But then we have the known one, which is going to be where relative to this? 11,511.15. So it would be above and to the left or the right. So it's at 507. We're at 506. So it'd be above and to the right.
We're at 511.
So the 511 is the up and down.
Okay, yeah, sorry. Those are switched.
Okay. So here's that point, which is 10,507.23, comma, 11,511.15. So the linear misclosure, if we zoom in, we really want to know the linear misclosure is the straight line distance. So just using Pythagorean theorem, if we do the delta x, delta y, add them together, square root, that should give us the linear misclosure. Yeah.
.39.
Any questions about traversing? So if it is a closed traverse, again, you can sum the departures and latitudes to calculate that linear misclosure. Also, whenever you go back through, you would be calculating the easting and the northing as your final step of the original point. You could also verify your error there. So the last topic they have is coordinate systems, and we don't really talk about that much in geomatics other than calculating coordinates of the traverse points. But like there's the state plane coordinate system, there's different types of coordinate systems, and there's methods to convert between different coordinate systems, but they don't give you any of that material in the FE exam. So I have no idea what type of question they could ask related to coordinate systems. I mean, you're all familiar with latitude and longitude and things like that, but I have no idea what types of questions they should ask, or they could ask, and I've never heard of any, and none of the review manuals have any example questions related to it either. So if you want to learn more about it, you can Google it. And so concludes the painful for everyone surveying review session, which will hopefully be better next year because I'm going to save all of these annotations. Good night and safe driving.